Well, hi everyone. Thanks for joining us today. My name is Dr. Jennifer Hanley. I am an astronomer at Lowell Observatory. And today I'm going to be talking about salts across the solar system. So life as we know it is pretty much, when we try and find it, we are looking for water, and liquid water across the solar system. So today I'm going to talk a little bit about how we can determine the stability of any liquid water, whether it's present, and how salts help with that story. So today I'm going to talk a little bit about Mars and Europa. And so here on the left we have an image of Columbus crater, which is a crater on Mars. And it's a really interesting crater because we think that it was a paleo lake, which means that it was a lake sometime in the past. And we think that because it has this salt ring around the edges of the crater. So it was a salty lake that, as it evaporated, left behind kind of a bathtub ring of salt as it evaporated. And so, I'll talk a little bit about how we find these salts, what they mean, both for Mars, and then also here on the right we have Europa. That's one of the moons of Jupiter. And it has a lot of salt on it and a lot of ice. And so we want to know what kind of salt it is. We think that the salt is this brown reddish material. So I'll talk a little bit about both of these things today. So going back, we know that there's a lot of evidence that Mars was wet in the past. We see this through these streamlined islands. So in both of these images, water would be flowing from the top to the bottom of the screen. You can see here as the water would come down, it hits this crater, it erodes away a little bit, flows around the crater, and deposits in a teardrop shape. And here on the right, we have these dendritic valley networks, similar to what you'd see here on Earth. For instance, in the Mississippi and Missouri river systems, you have a lot of tributaries that come and connect to one large river system. And then here's another example. We have these deltas, these beautiful deltas that we see on Mars, similar to again, the Mississippi River Delta. So it's coming from the left here into a crater. You have a river, and then as the river flows into a standing body of water, it deposits all that sediment that it was holding because it slows down. And here's a zoom in of this yellow box here. You can see a lot of these really distributary fans and these interesting features that show that we had a lot of water on Mars in the past. However, Mars doesn't support liquid water currently. So we have a phase diagram here of pure liquid water, and we have pressure on the y-axis and temperature on the x-axis. And so here on Earth, we have one atmosphere, and you can see here that when we get to 273 is where we go between ice and liquid, that transition. And then when we get to 373 or 100 Celsius, we would go from liquid to gas to boiling. So on Mars, the highest temperature is 20 degrees Celsius, 298 Kelvin. But that happens in the middle of the day, at the peak of summer, at the equator. So it doesn't happen very often or for very long. And it can get as cold as 120 Kelvin. That'd be in the poles in the winter. On average, we're about 220 Kelvin. So well below this freezing point. The other thing to consider, if we look at this diagram, we have the pressure on Mars is much lower than it is on Earth. So we have 0.006 atmospheres. And so you can see here that we don't even really extend into the liquid stability range. We have mostly just solid and gas, so ice and water vapor. So that's where salts come into this, and salts are really important to the stability of water. They can affect it by lowering the freezing temperature. That's why we salt roads in the winter. It actually increases the boiling point. That's why some suggest that you put salt into your pasta water because it actually increases the temperature that you're cooking at. And also, salts can lower the evaporation of water. So basically the salts preserve what liquid is present for a longer time. And just another way to look at that is from these different diagrams here. So this is pure water on Earth's surface. You see, of course, it freezes from liquid to ice at 0 Celsius, and it boils at 100 degrees Celsius. Unless you're here in Flagstaff, where we're up at 7,000 feet, and this is where that pressure that I talked about on the other phase diagram comes into play. Here in Flagstaff, the boiling point of water is about 93 degrees Celsius, and that's why they have all these, high altitude baking boats. So, looking at Mars, again, both the pressure and temperature are really important here. You see that water boils at 10 degrees on Mars because of the lower atmospheric pressure. However, if we add salt, and in particular one salt, magnesium perchlorate, which I'll discuss a little bit more here in a few minutes, we can extend the temperature range down to minus 67 Celsius for freezing and up to 24 degrees Celsius for boiling. So we can extend the stability range of that liquid by a large fraction on Mars' surface. So this is why I think salts are so interesting, and if we can find them and identify them, it can help tell us something about the stability of liquid water. So a concept I want to introduce is called activity of water, and it's something that helps us kind of make things equal or understand across different salts, because different salts affect the freezing point in different ways, but we can put these all in terms of the activity of water. The activity of water is something that ranges from 0 for no water or 1, which is just pure water. Anything in solution lowers the activity. Another interesting thing is that the relative humidity is directly related to the activity of water. Basically, how much water vapor the atmosphere is holding versus how much it can hold at a given temperature. So as I said, salts can affect the activity of water. Here's a little diagram showing how, if you recall, water is a polar molecule. So we have a positive side and a negative side, and that's affected by the ions in solution. We have a salt dissolved in water. It goes into its constituent ions, the cation positive or the anion negative, and those different ions can affect the activity of water in different ways. So different ions have different sizes, and so the bigger they are, the more they can disrupt water. And then also they have different charges. For instance, here sodium is a +1 and calcium is a +2. So those all affected in different ways. And then, of course, the concentration affects the activity of water. So the more of a salt or more ions we have dissolved into the water, the lower the activity. So to visualize that, this is a plot that I modeled here, how concentration of different ions affects the activity of water. So if we look here on the x-axis, that's the amount of water that we have. So we're starting with 1 kilogram or 1,000 grams of water. And as the experiment or the model goes, we go from left to right on the axis, and we're evaporating water. Here on the left, we have the concentration of the ions in that solution. So you can see here we're starting, all these different colors are different ions, and we're starting, between 0.1 and 10 millimolar of a concentration of a single ion. On the right, we have activity of water, and that's this thick black line here. So you can see at 1 kilogram here, we start at 1, the activity of water of 1. That's because it's not very concentrated. The solution is not very concentrated. So as we evaporate the water, as we go from left to right on the plot, we can see that the activity of water starts to drop as the concentration of the ions increases. And so you can see that it really starts to drop significantly down to almost an activity of 0.2, but we have less than 0.1 grams left. So it's kind of this interesting thing where, yes, you can get it very concentrated in the low activity, but you don't have a lot of water left. You have to really concentrate the ions to get to this low activity. And what's really great is that the activity of water can be directly tied to the freezing temperature. So again, we have the same plot here. We have mass of water on the x-axis, the activity of water on the right, and this is in blue now. But on the left now we have the freezing point, the temperature at which this solution will freeze. And so here you can see that at the 1 kilogram activity of water of 1, we have a freezing point of 273, which is what pure water is. Now, as we start to decrease the activity, we start to decrease the freezing point. You can see that if we get down to this 0.2 activity of water, we come across, and that's almost 100 Kelvin. That is a significant depression from 273 down to 100 Kelvin. But let's maybe take a more reasonable amount of water. Let's say, 1 gram here. We're at maybe, 0.6 activity? And that brings us up to about 220 Kelvin, which is, hey, that's exactly what the average temperature on Mars is. So you don't have to get all the way down to as low as you can go to depress the freezing point enough to actually get it to where we can have liquid water on Mars today. So talking a little bit about these different salts. So here's some chlorine anions, and we have chloride here on the left. That's probably what most people are familiar with, NaCl, halite, and that's just table salt. Hypochlorite, NaClO, that's actually common bleach, household bleach. And then the ones that I'll probably talk most about are the chloride, the chlorate, and the perchlorate, because those are the most stable. And actually, perchlorate, you can see, is really highly oxidized. It has a lot of oxygen attached to it, and so sometimes it's used as rocket fuel. So if we find it on Mars, maybe in significant quantities, we could potentially use that. But in the meantime, I'm more interested in the habitability aspect of it. So you have these anions, and when you associate them with the cations, you form the salts. So where do we find perchlorates and chlorates? So they've actually been found on Mars with NASA's Phoenix mission in the North Polar region of Mars. And it's also been found by the Curiosity rover in Gale Crater. On Earth, they're pretty rare. They pretty much only accumulate in hyper-arid, very, very dry regions, such as Antarctica, which, yes, is actually very dry, the Atacama Desert, and the U.S. Southwest. They tend to be formed through oxidation, so with the free oxygen radicals associating to a chlorine elemental atom through UV oxidation. So, as I've mentioned, different salts depress the freezing point by different amounts. And chlorine salts in general tend to have actually a lower freezing point than sulfates or carbonates. So if we look at here at this table, you can see that the sulfates, common sulfates like magnesium sulfate, is found throughout the solar system, but it only depresses the freezing point by 4 degrees. It doesn't do as much as some of the other salts, especially as we get down to looking at the perchlorate and chlorate salts here, magnesium perchlorate, calcium perchlorate, etc., which we can get down to almost 70 degrees depression or freezing. So just to kind of, again, show a visual representation of that, we have that magnesium perchlorate brine on Mars that I showed earlier compared to a magnesium sulfate brine. So if you recall, 10 was the point where it boils, pure water boils on Mars, and that's the same for magnesium sulfate. And again, it only depresses above -4. So you can see that differentiating between different salts is really important to understanding the stability range of liquid water. So coming back to some other things about salts, another thing is that salts and perchlorates in specific are extremely hygroscopic. That means they really like water. And that's best illustrated by a video. And what you're seeing here is a process called deliquescence. This is magnesium perchlorate, 6H2O, dry, so it's at 23 degrees Celsius in a 75% relative humidity chamber, and it's a time lapse, so it's 18-hour time lapse for the whole video. You can see what's happening is, so it starts out, the salt is white, just like you would see regular table salt as, and then it starts to actually absorb water vapor from the atmosphere and create a liquid. and it grows. It grows from right to left. You can see it actually dissolving the salt into a solution. So it's pretty incredible that you just have this dry salt. If it's humid enough, the salt can turn into a puddle. And depending on where you live, you might have experienced this. This is why they put rice in salt shakers to absorb the water, so that the salt doesn't stick together and clump up if it deliquesces. So for all these reasons, it's pretty interesting to think about where liquid water can exist throughout the solar system. But the trick is, can life live in these environments? And this is a whole topic of study by astrobiologists. They study different organisms called extremophiles, or extreme-loving organisms. Halophiles would be salt-loving. And it's interesting because a lot of the work done with activity of water has been done by the food industry, because they're actually trying to stop organism growth. So they're doing the opposite, that we're trying to find where life could exist at low activity. So some examples, though, the lowest known survival and actually cell division, so kind of one example of life, is 0.85 water activity. So I kind of pointed out before that 0.6 value, and that's a temperature of about 220 Kelvin. So we can get down to those levels. However, not all water activities are created equal. Different salts organisms react to the solutes in the water differently, right? So a magnesium chloride one at 0.6 might be different than the magnesium perchlorate. Maybe the organism likes the oxygen, or maybe it doesn't. So we need to look at all aspects of what life can survive, not just the water activity, but also temperature, the type of salt. Then there's also things like radiation environments, which we haven't actually found anything that can tolerate all of the conditions that we might find on Mars, but we're finding parts of it. So we see that microbial communities can thrive in magnesium chloride-rich brines at, between 0.75 and 0.63 activity of water. We find that we can actually get to slightly cold temperatures, minus 25 degrees Celsius in Antarctic, in a salty NaCl solution. And then there's organisms that can actually use the salt crust. So if we look at the picture in the background here, this is a halite crust. And there's been, pink Himalaya salt you might recognize from your kitchen. But so in the Atacama, there are these communities that can actually survive in these halite crusts. So they did a study, some of the people listed here, and it showed over 1 year, it rained once in the desert at their field site. So if the organisms needed pure water, they would have only had one rain event where it was liquid. However, the relative humidity got above the point necessary for the salts to deliquesce 76 times. And that's pretty remarkable. So the organisms living in these halite crusts were able to utilize those deliquescence events and actually get liquid water more frequently than if they had needed pure water. And last, there's some examples of perchlorate and chlorate-reducing bacteria. So using those extra oxygens as an energy source. So where are these salts and how widespread are they? How do we find them? So some of the work that I've been part of is looking at the spectra of these salts to try and identify them on various planetary bodies. So here we have a couple of different examples. So on the x-axis for both, we have from 1 to 2.5 microns. That's the near-infrared region of the spectrum. So what we're looking at when we look at these wavelengths is reflected sunlight. And so what happens is if it's reflected, it's at 1 and it's flat, if it's completely reflected. However, if there's some mineral present, it actually will absorb at a specific energy based on its molecular structure, and you'll have these absorption bands. And so based on these absorption bands, we can start to identify what minerals are present. So you can see here that all the salts that I'm showing, if they're hydrated, so if they have water on them, you see water features. So we have this 1.4 OH band here, and the H2O region here, so at 1.9. So these are two pretty important ones for looking for hydrated minerals across the solar system. So I was funded by NASA to go and look for these core cells. So these are spectra that I collected in my lab, and we wanted to go and apply it to data that was collected by some of the Mars missions. So we went back to Columbus Crater, which I showed you at the beginning. And so again, we have this nice salt ring. And so if we zoom in on one of them, one spot here, you can see again, here's the salt ring. And we started to actually try and parameterize the spectra. So we're looking at the depth of that 1.9 water feature. And you can see here that we have varying depths. So what we did is kind of combined different parameters. So we're looking at a 2.2 band perhaps, or in this case, this 2.4 shoulder. Briefly, if you have more questions, please let me know. But here we're combining a couple different parameters. So we have the 2.4 shoulder plus the 1.75 band, and that allows us to pick out interesting spectra and compare it to our laboratory results and identify what salts are present. So another thing to keep in mind is that temperature actually affects the spectral features of minerals, in particular hydrated salts. So here we have 3 pairs of spectra. So we have magnesium chloride 2H2O at the top. The topmost one is at 80 Kelvin, and the second one is at 298 Kelvin, basically room temperature. And then the next pair is the 4H2O, and then the bottom pair is the 6H2O. So in each case, we have the 80 Kelvin right above the room temperature one. And so this goes from 0.5 to 2.5 microns wavelength. And so what I really want to point out here is how much the spectra changes when you reduce the temperature. So here, this feature, let's look at the 1.25 feature of the magnesium chloride 6H2O. You see it kind of just is flat and then dips down again. Whereas you go to 80 Kelvin, it turns into a more pronounced band, and it actually has 3 distinct bumps in it. So we're actually resolving the vibrational modes of each of these water molecule pairs. So this is important because a lot of the spectra, so to identify the minerals, we have to have laboratory or reference spectra. And it's important to collect the spectra under the circumstances on which you expect to find the minerals, even on the surface. So for instance, Europa, if we're talking about going to cooler temperatures, the average temperature is 100 Kelvin on Europa. And so we really want to get temperatures close as possible to what you'd find there. Here, if we're looking at Europa, we can see the albedo here on the left versus the amount of supposed non-icy material on the right. And so Europa is really icy, but it has this wrench component that I showed from the beginning. And this is associated with the darker materials. And so you can see here that the, quote, non-icy material, which is probably hydrated salts, tends to correlate really well with that darker material. So identifying salts on these icy satellites is really important, and we can make some hypotheses as to what we expect to find there. Based on the temperature and the amount of water present, we might expect that you'd have higher hydration states of these different salts. For instance, the 6H2O instead of the 2H2O. However, some experiments show that radiation might actually break those bonds, and maybe it goes into a lower hydrated form. Also, it's possible that Europa's environment might actually exchange some of the salts. So maybe it's changing out from a magnesium chlorine that came from the ocean, but it's getting implanted with sulfur ions from Io, and it turns into a sulfate. So identifying where and what type of salt is present, in addition to the hydration state, is really important for understanding the history of the surface and where it was implanted from and where the salts came from, and radiation history. So habitability from that aspect, and then also habitability from the salt stability aspect. And speaking of that, as I've mentioned now a couple times, different salts lower the freezing point by different amounts. And in Europa's case, what that means is that sulfates tend to have a warmer freezing point, which means we probably have a warmer ocean and probably have a thinner ice crust. However, chlorine salts would have a lower freezing point, so based on modeling, would probably mean a colder ocean and a thicker ice crust. So this is kind of a catch-22 for us, because we really want to see this extended range of liquids, right? So we want to get liquids all the way down to these really cold temperatures that we see in the outer solar system. But can life survive that? Are the conditions that get to that liquid habitable? So trying to look and see if we see these chlorine salts on Europa. Here's some results from Leger et al. They used the Very Large Telescope to look at the composition. So they did spectral mapping, and you can see here that here we have a visible stretched globe of Europa from Galileo and Voyager. You can see again, here's that darker material that I showed in the other image. And the magnesium perchlorate and magnesium chloride, when you combine them, tend to align with this darker region. So this is something that I want to look into a little bit further, see if we can pick out any variations, temporal variations, and then also look into the different wavelength regions as well, and utilize some of the lab spectra that I've collected to look at Europa. So I'll be using the Lowell Discovery Telescope and the Night and Express instruments, so that's near infrared and visible, or optical wavelengths, to look at Europa and see how it's changing and what we can figure out about it and its habitability. So to summarize, chlorine salts are very important for the habitability of these different planetary bodies. Chlorine salts do appear to be globally distributed across Mars. In Europa, the non-icy, non-sulfuric acid component probably includes chlorine salts. Stay tuned, I'll be continuing to look at this. I didn't mention this, but just as an aside, salts have been detected on other planetary bodies, such as Enceladus and Ceres. The big take-home point that I want to get across is that it's really important to differentiate the type of salts that are present so that we can understand the stability of water and its habitability. So for modern sites, this would mean, specifically if the salt is there, what does it mean for the salt stability, for the water stability at present? But it can also tell something about the history. So of the lake, what kind of salts were in the lake? Was that lake potentially habitable to life, even if it might not be today? So I would like to thank all of the many collaborators that have gone into all of these projects. There are a lot of projects listed over many years, as well as various funding agencies. And with that, I will say thank you and take any questions. Okay, so we have a couple questions already. Great. Tom C. asks, will the salts be primarily associated with sedimentary rocks? That's a good question. So when salts are typically formed, they're formed from leaching of groundwater over different rocks, but it doesn't have to be sedimentary rocks. The salts, so sedimentary rocks and salts are kind of formed in similar ways a little bit, where you have water present. but I don't think they're necessarily correlated with each other. Well, maybe correlated, but they're not formed at the same time. So salts are formed once you have everything left over and the salt or the water evaporates entirely away, or you have like a crust or something like that. Typically, sedimentary rocks and salts are not forming at the same time, although they might be in similar regions. Let's see. Jim Davies asks, is any fresh water found elsewhere in the solar system? No. Well, liquid water, no. We see Europa there looks to be a lot of almost pure water ice on the surface, not mixed with salt. And that's actually a little puzzling. How did the ice form? Probably through freezing of a salty ocean. So that it can actually make sense to have pure ice form as you're freezing. But potentially there's eruptions of a plume, so you could deposit salty water, salty ice on top of that. We see a lot of pure water ice on Mars. It seems to be that when we do see where we see water ice, it's mostly pure. Pure liquid water, no, we don't see that so much though. He also asks, do salts always show up in pictures as lighter colors? No, not necessarily. So in the Mars image, we saw that the salt looked pretty white, but on Europa, it was a reddish material. And so it kind of depends on what it's in contact with and how it's formed, and basically just the contrast between the different materials present. And then it seems to be that on Europa, the salts are probably irradiated in some way, which does tend to make them a more reddish color too. GKC Geoscience asks, are there any Martian craters that show evidence of multiple episodes of filling and evaporation? I'm not sure that we can necessarily say multiple episodes of filling and evaporation, but very likely. So we see a lot of chloride deposits in the southern hemisphere that look to be forming through groundwater evaporation. So you had just kind of standing water where the groundwater, through seasons or, different climatic events would kind of raise and lower. And so we end up with these kind of like the Great Salt Lake desert, where it's just kind of very, very flat salt remnants. And so that would be multiple episodes of dissolution and then efflorescence, or the forming of salts. It's very, very likely that there were craters that show that have multiple episodes of filling and evaporation. We see that evidence. I guess we see that evidence through other means, not through the salts, though. Now that I'm thinking it through. So yes, we do. Michael West asks, are salts found in asteroids or meteorites that hit Earth? And are there implications for panspermia? Would this play any role in survivability of microbes journeying through space? That's a good question. So yes, we do see salts in asteroids and meteorites that hit the Earth. I'm not sure, that's not my area of expertise, how widespread it is, but I do know that they have been found. It's an interesting question about panspermia. You could envision that maybe a salt would encourage a microbe to I'm thinking of it more in a desiccation way, where it goes into a spore-like state or something like that. But as far as the availability of water and using that, I think you kind of need an atmosphere or a water source, right? So some amount of ice or water vapor in the atmosphere to get any liquid from the salt in the first place. So the salt, unless it's undergoing changes in temperature and relative humidity, you're not going to get it to give water to any microorganisms while they're hurtling through space. Jonathan Ford asks, can we find salts on Pluto? We have not found salts on Pluto. I'm trying to think. Maybe ammonia chloride might be. Maybe. We know that there's ammonia, ice, ammonia water hydrates. So typically, we're probably not going to find too many salts on Pluto. It's also much too cold to actually get water, our type of water, to be liquid at those temperatures. So Pluto is 40 to 50 Kelvin. That's much, much colder than any of the salts or any of the activity that we saw that at the lowest at 0.2, we were at 50 Kelvin. You needed a very, very, very concentrated solution to do that. However, that being said, there's some interesting analogs out in the outer solar system. For instance, when you mix nitrogen with methane or ethane and methane ice together, you can actually get a depression in the freezing point, similar to how you would with salt and water. So that's actually something that we're working on in the Astrophysical Materials Laboratory at Northern Arizona University. And so, yeah, that's really exciting. It's an interesting question. We're not going to find salts there, but we might be able to find a way where we can get liquids. And who knows what life could have figured out that way. Okay, so Tom C asks a follow-up. If igneous rocks contain the needed salts, or contain them after some tectonic time, have the Mars meteorites shown any of the particular salts? I believe, if I am remembering correctly, so don't take it as, I'd have to look it up, but I believe they did have found perchlorate in one of the Martian meteorites, perchlorate and chlorate, in fact. I think. Let's see. Keith Holinsky says, it would be interesting to know chlorine salt concentrations throughout our solar system over time. Yeah, so chlorine is an interesting element, and if we start to think about how likely is it that we actually find chlorine salts across the solar system versus, for instance, sulfate salts? So if you look at the elemental abundance of our solar system, we expect actually sulfur to be more prevalent than chlorine. And so we do actually expect sulfate salts to probably be more common than chlorine salts. I just think chlorine salts are a little more interesting because they extend the stability range by a larger amount. And we do expect chlorine to be present elementally in the initial starting material of most of the rocky solar system bodies. So there's a whole host of processes that go on between, the supernova and elemental formation of the chlorine and the sulfur, to all the way to differentiation of these rocky bodies, to water and rock interactions that actually leach the chlorine and the sulfur out of the rock, and also the sodium and the magnesium. So whatever your starting material is, that's where you're getting your different ions from. And then those can combine together to form different salts. So I don't have an answer about what the concentrations would be throughout the solar system over time. However, with more water-rock interactions, we will increase the amount of salts present. So I'm at the end of my questions. If anyone has anything else, okay. Well, thank you so much, everyone, for joining in. And please keep in touch. I have my Twitter and email handles there. And thank you so much. And I'll talk to you soon, I'm sure. Bye.